My name is Leonor, and I'm going to be talking about the study we did on the simulation of future scenarios of the marine ecosystem in the Azores. So the Azores, as Inês has already spoken about yesterday, is an oceanic archipelago, a Portuguese archipelago, which has a very large EEZ. And I just brought out these three graphs because I wanted to show this kind of frontier which lies in the middle of the archipelago, where we see so colder waters in the north, less saline and more productive, and warmer waters in the south and less productive. So we really see like this line between more temperate waters in the north and more oligotrophic waters in the south. And we can ask ourselves what is going to happen in the face of climate change. Like, how is this going to change? Are we going to be is the Azores going to become more oligotrophic, and what is this going to mean for the ecosystems? And another thing that the Azores has is fisheries. And as Inês mentioned yesterday, fisheries there are very culturally important. But as Mary said, actually the numbers of employed people are quite small, like 13,000, I think you said. And they remain mainly artisanal. The most important fisheries are bottom long line, which targets demersal fish, pollen line, which targets tuna, and foreign pelagic long lines, which target other species of migratory fish. And so it was kind of with, and we can ask also how is fisheries going to play out in regards with climate change. So it was a bit these questions that we wanted to answer. So how the system is going to evolve, what is it going to mean for its health, how is it going to play out with fisheries, and what are the main drivers of these changes. So for that, we configured the Strathi2E model to the Azores region. We simulated some climate scenarios. We examined some ecosystem indicators to look at the health of the system. And we simulated fishing scenarios. We did a sensitivity analysis to look at the main drivers of change. So you already all know the Strathi2E model. It's an end-to-end model of 26 guilds. It's coupling an ecological model and a fishing fleet model. The ecology model has inputs such as physical parameters, biological parameters, and target data to fit the model. And the fishing fleet model can simulate up to 12 fishing fleets, and it has inputs such as activity rates, spatial distribution, processing rates, and discard rates. The driving data are hydrodynamic data, sunlight, temperature, suspended sediment, river nutrients, and atmospheric inputs. And most of these data were outputs of the NEMO RSM. And that was forced by two Earth system models, GFDL and CNRM, under two climate scenarios, SSP1, which is a more conservative, sustainable scenario, and SSP3, which is a less so scenario. And in 6 decades, so from 2010 to 2060, given 24 model variants, as we saw before. So these are the results we got for some of the guilds, how these guilds evolved throughout the decades. And we can see, so in blue is the SSP1, in red is the SSP3. The solid line is the CNRM model, and the dotted line is the GFDL model. And we see a general decline across almost all guilds. The most affected guilds are the demersal fish, which see a decline of around 80% until the 2060s, and the birds that, as for the St. Helena study case, decreased to almost 99%. And we see that both climate scenarios and GFDL model kind of show a similar trajectory. In terms of ecosystem health, we see a reduction in the mean trophic level, a small reduction in the mean trophic level. Then, if we look at ascendancy, so ascendancy reflects the organization of the system. It shows a decrease. Overhead represents the redundancy and the capacity of the system to rebound after a disturbance. Also shows a big decrease. Effective connectance, which represents the links, the strength of the links in the ecosystem, also sees a decrease. And then if we look at the Fogarty index, which is basically the exploitation rates of the system, there is an increase in the exploitation, although there is actually less landings in the overall system. Then we wanted to see what the impact of the fisheries would be. So we added some fishing scenarios, and we have the baseline scenario, which basically keeps the fishing as it was in the 2010s decade, a no fishing scenario, which removes all fishing activity as kind of a best case scenario, and then narrative-driven scenario, so which is aligned with both SSPs. So the OSP1, which is Ocean Shared Pathway 1, establishes MPAs as they were designed in this 30 by 30. So the new MPAs that were set in the Azores, and prohibits two gears, the pelagic and bottom long line, because these are associated with a high bycatch of sharks. And then the OSP3, which is more aligned with SSP3, sees an increase of 5-fold in all fishing activities. And so this is the results we got. So in the left we see only the impact of climate scenario for migratory fish, planktivorous fish, and demersal fish. The striped line is the GFDL, and the solid one is CNRM, blue SSP1, red SSP3. Then we see only the impact of the fishery scenario, so the no fishing, the OSP1, which is only assessed for the SSP1, and the OSP3, and then the combined impacts of the climate and the fishery scenario. And so what we see is that for migratory fish, climate seems to have a small impact on this guild, but fishery scenario have a big impact. So the no fishing increases its biomass by around 50%, while a big increase in fishing activity, so OSP3, sees a large reduction in migratory fish biomass. And when we look at the combined effect of climate and fisheries, we see that actually it's largely fisheries that are governing these changes. Then if we look at planktivorous fish, we see that the fishery scenario are not impacting that much the fishing guild. The changes are very close to zero. And then when we look at the combined effects, it's mostly climate that is governing these changes. And same for demersal fish. So the impact of the fishery scenarios are actually quite small compared to the, sorry, of the fishery scenarios are quite small compared to the climate scenarios. Then we looked at so we did a sensitivity analysis to look at what were the main external drivers that were impacting the biomass of most guilds, and what we saw is that nitrate came out as the most important driver for almost all guilds. Same as, well, yeah, nitrate was the biggest one, but also upwelling, surface temperature, and vertical diffusivity. And because it was because nitrate was the main external driver for most guilds, we can see that this is kind of a bottom-up cascade affecting the whole system. So this is the takeaway message. Climate appears to be the key driver of change in the Azores ecosystem, causing a bottom-up cascade primarily driven by nitrate declines. Fisheries for most gills appears not to have a reduced effect, not for migratory fish. And of course, it's important to say that this is for the whole gills and not for specific species, of course. And I think the takeaway message is that it's really important to integrate climate change when making decisions regarding management plans. So yes, thank you very much.
Thank you, Leonor. We have time for questions. Martin has a question. Martin.
So thanks a lot. And so what I take from this is that you generally see a very strong response to climate change, but less so in terms of fishing. And since I followed your work also for your master's, I remember the historical or the current fishing pressure asserted by the more artisanal communities rather low in terms of. So for this fishing scenario, you made that OSP3 whatever. Was that a five-fold increase from the baseline?
Exactly. Yeah. From the baseline.
So what would happen if you would ramp it up dramatically? Because if you ramp up from 5 point from something very little, it doesn't really amount to a very high catch rate. While the migratory fish, I guess this is where there's quite a higher overall exploitation rate because it's more of a commercial fishery. So what would your thought would be if you significantly ramp up that fishing pressure asserted by the artisanal fishermen?
Yeah, I think, well, our way of thinking was also to do something that was realistic. So I guess if it's small, I mean, it's not like it's going to change by, it's not going to increase by 1,000. I know. So we like also considering the population and everything. So that's why we just did a 5-time increase and not go overboard with it. But I guess we would see like more significant changes if we would increase it some more. But yeah, that was kind of our thought process.
I think it's just important to note somewhere that this is relative to the actual fishing pressure.
Right.
So that you don't give the impression that fishing doesn't play a role at all in this kind of system. I think surely it would.
There's another question by Dave.
I was really struck by the role that nitrogen input played in both the last two presentations in very different ecosystems. But the similarity, I guess, is it's deep water feeding into shallow water. I just wondered if that interpretation was confirmed from any other model or data.
Well, I saw a few other studies that that showed that nutrients played a large role, and there were some experiments done in the Azores where they depleted some nitrates and it had a big effect on the system. So I guess, there's a few other studies on it, but not a lot.
One more question, Mike over there.
Mike's going to answer mine.
I am. Exactly. I mean, there's a global natural experiment. Look at the global upwelling systems, the Benguela and off Chile. They're entirely driven by injection of nitrate from deep water, and the productivity is through the roof compared to the systems that we're looking at here.
We can have one more question before coffee break. Benjamin.
It's a comment also following up on the nitrate story. So in the Norwegian Sea, silicate is also a very important driver. And I know from a number of experiments with different physical models, that leads to quite drastic differences in result on primary production. And in the Barents Sea, there was a study a few years ago using 3 different models. And one was projecting increase in primary production, the other one decrease, and the third one no change. And that's because of slight differences in the physics, but that have huge implication on the stratification that is actually driving the primary production. So overall, these models are not frankly different, but the small differences they have a big impact on the biology. So here, this is a critical question. I think it's we have to be careful. The models are maybe validated on the physical side, but maybe not on the processes that are really critical for the primary production. So it's really something to check.
Sorry. No, I totally agree. And one thing also coming back from to the discussion yesterday and a bit today about the complex versus simple messages, but also model. And I think that we were talking with Tanguy yesterday about that in the Nemo model in that area, because we have more than one group of phytoplankton, we actually see that diatoms are going down, but the other groups are going up. And so in total, we actually have more phytoplankton, and this was not seen in strategy 2E exactly because they are built differently. And that's totally get the point that there is a lot of uncertainty in the biogeochemical model, and that's why we're trying to, as a community of biogeochemical modeler, we're trying to push more and more that we need to do ensemble because we need to try to factor in as much as possible. The unfortunate thing is that those bases are expensive to run, and so it needs a lot more coordinated effort to do that.
It's not the first time that the models or the exercises tell us that the model selection is more important than the scenarios. In several cases, that's why ensembling model is a way to go. Okay, we can take another question or go for coffee break. Thank you very much,
Thank you.
Leonor. And we should be back 5 to 11.